Hello, Edina Intermediate Algebra students. Today we are covering the first section of our very first topic, which is topic 3, section 1. And we're going to talk about two vocab words that are going to show up throughout the school year, domain and range. At the end of 3.1, we should be able to answer the question of what is a function and how are domain and range important when dealing with a function. Before we get too far, let's just discuss some really good watching recommendations. This is a video, so you have the ability to pause the video at any point to write down ideas that you want to remember. You also could pause, and I'll direct you to do so, to try some of these problems on your own. Make sure if you pause, you can absolutely rewind the video to watch it again if you didn't understand it, or if I move too quickly. Lastly, take notes. It's a lot like if we were in class. These are the important concepts from this section. At the end of the video, I will have a note sheet with some important concepts that I created. You don't have to copy it down, but I recommend that you copy it down or at least look at it to fill in your own notes or to capture some of the main ideas that maybe you missed while going through the video. Let's get started. So we're going to start by just thinking about this machine that I have here. And you guys know about machines. When you put something into a machine, something will come out and the machine does its magic, right? So if I put a Keurig cup in my coffee maker and I press a button, out comes some coffee. Well, for this particular machine, we're going to use the rule that the output, or what comes out of it, is the first letter of whatever word I put in. So for example, if I was to put in the word math, the first letter is going to come out of the machine, which is M. If I was to put in the word zebra, out would come the first letter, which is Z. Now we could keep going, but that's kind of hard to keep track of. So I'm going to create this table, and I'm going to write down everything that I put in and what comes out with it. So we already talked about math, and we already talked about zebra. What would come out if I put the word school into my machine? Out would come an S. If I put the word Edina in, the first letter would be E. And lastly, if I put the word music in, out would come another M. What we just created was something called a function table. A function table just lists out all of the inputs and outputs that you get when you use that function machine. There's another way of representing this information as well, and that's with using something called a mapping. A mapping is where instead of creating a very boxy table, we create some bubbles. And usually on the left-hand side, we write out our inputs, so the same words that I put into my function. And on the right-hand side, I list out my outputs. Now, something doesn't seem to line up here, but that's because I will not write my repeated inputs or outputs if I have any. Once we have this, we need to tell whoever's reading this which input goes to which output. So math would go to the letter M, so I draw an arrow. Zebra goes to Z, school goes to S, Edina goes to E, and then music goes to M, so I draw an arrow back up to that M. And that's why you don't necessarily need to have repeats. In math, we don't always use input and output, although that often makes more sense. Instead, we're going to introduce these words called domain and range. But what they are is exactly the same thing as input and output. Domain is our input, just another fancy word for it, and range is our output. And we'll summarize this on a later page. Let's look at another function table, this time utilizing numbers. So here, my input was the number 1, and out came a negative 1. In went a 2, and out came a negative 2. You can pretty much guess the pattern, I would imagine. Showing that using a mapping, here are my input values, 1, 2, 3, 4, and 5. Here are my output values, all the negatives of them, and then I draw an arrow that shows which input goes to which output. Now, since we are dealing with more numerical values, which we're going to get into more in class as well, I can also represent this information by calling it not only domain and range, but I can say that my domain is my X values and my range corresponds to my Y values. So there's one last way that we can write this relationship, and that's by writing out ordered pairs. I'm going to use what we call in math set notation. And what set notation is I'm going to list out all the ordered pairs in these little mustache brackets or squiggly brackets, as some might call them. So one of my ordered pairs, or one of my input-output, is going to be 1, -1. So I'm going to write that as a parenthesis 1, -1. Now I'm going to list out all of my ordered pairs. So I'm just going to put a comma in between my next set, which is going to be my next pair of input-output, 2, -2. And I'm going to keep listing out these input-output pairs in this set notation. So 4, -4, and then 5, -5. Now, in order to close this up, I'm just going to finish it with that mustache bracket. This is just listing out a set of ordered pairs or input-output pairs within those mustache brackets to kind of keep it as a nice group. So let's summarize some of these ideas. We introduced this word domain. Well, domain is the exact same thing as saying the input of a function. So what do I put into my function machine is what's going to give me my domain. These also correspond to the X values when we're starting to deal more with algebraic ideas. The range is the same thing as the output of the function, which also corresponds to our Y values when we're dealing with more algebraic thinking. So let's do a couple examples. Identify the domain and range. So here I have a table and I have a graph. So the table, if you remember, X corresponds to input, which is the same thing as our domain. So I am going to use set notation again, and I'm just going to list out the members of my domain or my X values. So I have a 1, 2, a 3, a 4, and a 5, and I'm going to close that mustache bracket. The range is the same thing as our Y's. So this is the same thing as output, which is the same thing as our range, our Y values. So I'm going to list those out in set notation. Looks like an 11, and then a 12, and then a 13. Now the next one is a 13, and then a 13 again. And so I don't have to rewrite those. I can just write them one time. So there's my domain and my range. Looking at the graph we have as an example, I have a set of points. Now, we talked about this at the beginning of the school year, but one thing I would suggest is potentially writing out what the ordered pairs are. So this point is -2, -3, then I have -1, 1. I have this point right here, which is 0, 0. Here I have to go over, let's see, 1, 2, 3, and up 4. And then this one also goes over 3 and up 5. I like to write them as ordered pairs because then it's a little easier for me to see my domain and my range. My domain are all my X values, so -2, -1, 0, and 3. Again, I don't have to repeat those. And my range are all my Y values, which are -3, 0, 1, 4, and 5. As a reminder, when you have your points, they are always listed as X and Y. So make sure you keep those clear that that is our range for our Y and the X is your domain. On this next screen, I'm going to have you try a couple on your own. So be prepared to pause the video and try. This time we have a mapping and another graph. I'd like you to identify the domain and range. So please pause the video and revisit us when you have your answer and can check it with what we got. Welcome back. Hopefully you got these same answers as you were listing out your domain and ranges. The mapping is quite easy because they're separated by those two separate bubbles. The graph a little bit more difficult, which again, I would highly recommend writing those out as ordered pairs or points in order to figure out the X values and the Y values, otherwise known as the domain and range. Let's think about this. So yesterday we talked about inputs and outputs. So here's an example that you probably would be familiar with. If I used my function machine and my rule was the output will be the number of sides, I bet you we could fill out this table. If I put in triangle into my function machine, how many sides would come out, or what would be my output? Well, a triangle has 3 sides. We all know that. How many sides does a square have? 4. How many sides does a pentagon have? 5. A hexagon has 6. This one, don't fall into the trap. An octagon is a stop sign, so that one actually has 8. Seems pretty easy, right? This is a function machine. What would you think if I changed this table up a little bit, though? And what if we lived in a world where we inputted a triangle and out we got 3 or 4 sides? Like a triangle could have both 3 and 4 sides. Wait, that doesn't seem to make sense. Or what if a square happened to have 4 or 5 sides? Like it could be either one. Or let's think about a phone number. You dial your best friend's phone number, and sometimes you get your best friend that answers, then sometimes it's your worst enemy that answers. Like that's not what happens. Your phone number goes to that one particular person. So something's a little bit off with this table. What's happening is we have inputs in this example that are going to multiple different outputs. This does not work in functions. This is not a function. What this is an example of one input to many outputs, which is not the definition of a function. And a lot of times they will seem weird in the scenarios. The definition of a function, and this is something you're absolutely going to want to make sure you know, is every input, aka your X values, has exactly one output, which are your Y values. So this is an example right here of something that is 1 to 1. One input goes to exactly one output. Now, something can be a function and not be 1 to 1. And here's an example of that. We might have an input that's going to an output, and then another input that's going to the same output. This is actually still a function because my input, this particular input, only goes to one output. And this input only goes to one output. And that's fine. We cannot have it going the other way around. And we'll show lots of examples of this. This is an example of many to one. These phrases, 1 to 1, many to 1, 1 to many, all those, you're going to see them when you're doing your homework assignments and as we're talking, but it's not something you'll necessarily be tested on. So here are 2 examples of, they're the exact same thing, but this is a function. So I wanted to show you in multiple representations. Here we have it in a table, and here we have it again in a mapping. We're showing the exact same thing. So -2 goes to 4, -1 goes to -2, and so on and so forth. Some things I want you to note is that we have one arrow going from each and every input value. So this is a function because every input has exactly one output. You will see this phrase again in Pearson when you're doing your work. Y is a function of X. So Y is the output. It makes sense because every X corresponds to exactly one Y. Here is an example of something that is not a function. All right, so again, multiple representations. We have a table and the mapping. The mapping, I think, is visually easier to tell because if you look here, -2, that is going to both -4 and +4, right? That's not allowed. That would be like a triangle having 2 different numbers of sides. It doesn't make sense. Same thing with this -1, right? In order for something to not be a function, it just has to happen one time where that you have that split. If we're looking at the table, something to notice is you see how you have these repeating x values. That is going to be a big clue that this is not a function, because -2 is going to two different y values. So we can say this in a sentence similar to what we did before, or we can say y is not a function of x. Y is not an output of x, because at least one x value corresponds to more than one y. They have to be exactly one in order to be a function. Let's look at the graphs of these two examples that I just did. So this first graph is an example of a function, or the one that I had just earlier. Notice it looks a lot like kind of a diagonal line if I was to connect those. And then the one on the right, we have what looks like somewhat of a sideways V. The first one is a function, and the second one is not a function. What do you notice, and what do you wonder? Now, I don't know about you, but one thing that I notice about that second graph is that I have these two x values that are lined up right on top of each other. And I don't have that happening in this first example. All these points are just the only ones in that line. And that's exactly what we want you to notice. This is something called the vertical line test. We are not allowed to have 2 points that line up on the same line, because that means that this x value has two different outputs, or two different y values. So here are some more examples using the vertical line test. Let's look at graph A. We have this V. Do we have any points that line up directly above each other? So I'm just going to imagine me drawing this line or pulling this line across. Every single point or place on this graph, there's only one part or one point that crosses. So that is a function. If I look at letter B, let's say I drew a line right there. I have 1, 2, 3, 4, 5, 6 places where those points are all lined up vertically with each other. That is not okay. That means there's multiple outputs for that input. Letter C, any place I draw a line, vertical line, that's the only point that shows up. So letter C is also a function. Why don't you try to answer the last three by pausing the video and taking a second to think, and then check your answers when you're done. Function and E and F were not. You're absolutely correct. Remember, if we have 2 points that line up right above each other, that makes it not a function. So just to summarize some of this information, and again, there will be a note sheet at the end, but you could copy this down in your notes. These are some hints as to whether something is or is not a function based on the different representations. So we have table, mapping, and graph. On the right-hand side, all of these are functions, examples of functions. And on the left, these are all not functions. So take a second to read through this slide, write it down in your notes so that you can use this as an example as you're doing your homework. Here are 4 examples of relations or points or ordered pairs. And I want you to think about those ideas or those representation rules we had on the last slide and determine which of these relations are functions. Which ones of these do we have every input going to exactly one output? Pause the video, give it a whirl, and come back to check your answers. Answers. Letter A is a function because you don't have any repeating x values. And if you need to, you could always draw a mapping that represents that if it's easier for you to see. Letter C is not a function. Here we have repeating x values. So 3 goes to both -10 and -20, which makes it not a function. B is a function, very clear to see. This is also very clearly 1-to-1. If you were curious, I spelled that wrong. 1-to-1, because you have one arrow from the input going to one output. And then letter D is not a function because it does not pass that vertical line test. You have 2 points that are lined up on top of each other.